Hello and welcome to Calculus 1, Lesson 1C.2, End Behavior, Part 1. 1C is actually going to have 3 parts in it instead of 2. Okay, so end behavior. End behavior is the behavior of a function toward the end of an infinite interval, such as c to infinity, infinity to c, or infinity to infinity. In a pre-calc class, you'd probably studied that as far as polynomials are concerned, because for polynomials, it's relatively simple. It's going to depend on your degree and your leading coefficient. Let's suppose your degree is even, and let's look at whether your leading coefficient is positive or negative. When you have an even degree and negative coefficient, you get frowning behavior. It's going to point down as x gets large in either direction. There might be whatever squiggling along the way, but eventually it's going to go down in both directions. With a positive leading coefficient, it's the opposite. You have smiling behavior. Again, it might have some squiggling along the way in the middle, but as x gets large in either direction, it's eventually going to go up. How about if the degree is odd? Well, even degrees eat negatives, right? So even degrees will eat negatives, odd degrees will keep it. So when x is a large negative number here, x to the fourth is still positive. That's why we get that smiling and frowning behavior. When your degree is odd, it will obey the sign of whatever x you're putting in. Okay, so when x is a large negative number here, x to the fifth will also be a large negative number. Okay, so large negative number times negative 7 is going to be positive. Other direction, if x is a large positive number, then negative 7x to the fifth is a large negative number. And if you picture, like, the silly things you can do with your arms if you're like trying to walk like an Egyptian, or maybe you've seen the music video for a song called Walk Like an Egyptian. You can see what I mean by, like, this has Egyptian end behavior. It's just a silly thing. And this is an ME term, by the way. This isn't, if you say this to other math teachers, they probably won't know what you're talking about. Again, this can squiggle along the way in any kind of way that a polynomial can. Opposite here. So if x is a large negative number, right here, then x to the ninth is still negative, times 5 is still negative. And then if x is positive, everything stays positive, with that potential squiggling in between. All right. So this is something that might be familiar. You might have studied end behavior of polynomials before. But now we want to try to put limit language to this idea. How do we use limits to talk about this? I'm still going to make a distinction between the even degree and the odd degree, positive coefficient and negative coefficient. We're going to talk about limits as x goes to infinity. Okay, so as x goes to negative infinity, when x is a large negative number, I get a large positive number for x to the fourth times a negative. So overall it's negative. When x is a large negative number, this quantity, negative 2x to the fourth, is going to be negative. And that is going to decrease without bound. However, when x is positive, we have a big positive number for x. Okay, we still have a positive number here times negative, and so that is still negative, and that's how you get the frown. What if the leading coefficient is positive instead? For example, with 3x to the 6th. When x is a large negative number, x to the 6th is still positive. Times 3 is positive. This will go to positive infinity. When x is a large positive number, all of that is definitely positive. And so you get the smiling behavior. Now let's talk about odd degrees. All right, let's be careful with our signs here. Negative large x, so large negative number in x to the 5th is still large negative. And then times -7, it becomes positive. So this is positive, and then, ooh, it's going to be the opposite here. X to the 5th will be positive when you put in positive numbers, times -7, so this is negative infinity. And here it is with a positive coefficient. As x approaches negative infinity, we're thinking about large negative numbers. So 5 times a large negative number is still going to be a large negative number. So this will go to negative infinity. And then when x is going to positive infinity, everything here is positive. So that's positive. All right. So now we can use limits going to infinity to talk about the end behavior of polynomial functions. How about rational functions? We're going to consider the function 3x squared over x squared plus 1. Let's see if we can figure out what the limit as f of x goes to plus or minus infinity is going to be. First, I'll have us look at this graphically and numerically. So here's our graph. As x goes to, there we go. As x goes to positive infinity, this is starting to look like a straight line. What straight line exactly? Y equals 3, right? It looks like we're going to have a horizontal asymptote at y equals 3. And that seems to be happening in both directions. Okay? So let me make a note of that. The graphical makes it look like we have a horizontal asymptote, y equals 3. Numerical approach would be looking at a table of values. There. Okay, so here is x, and then here is the y value, the same f of x that we're looking at. Okay, numerical approach says, let's watch what happens when x gets bigger and bigger and bigger. By the time we get to 100 for our x value, your y value is already 2.999, very, very close to 3. And then maybe try this with more zeros. 2.999. More zeros I put in, the closer to 3 it gets. So the numerical is going to support the idea that we've got a horizontal asymptote y equals 3. We could also look at that going in the negative direction, and you'll get the same results. In fact, we know that we will because this is an even function, right? All of the x's appear with a squared, so this function is actually even, which means it's sufficient to look at it in the positive direction only. Okay, so that's graphically and numerically, but when you just look at something by, like when you determine something just by looking at a graph or a table of values, you're technically not doing calculus. Technically, you're just doing algebra or pre-calc there. Let's try an analytical approach instead. Okay, one fact that we need in order to tackle this problem is when n is a whole number, when n is, you know, a reasonable power on x that you would find in a polynomial or rational function, the limit as x goes to infinity of 1 over x to the n equals, well, what's going on here? We have 1 over a very, very, very large positive number. And 1 over a large number is a small number. That's going to go to 0. So I'm going to use a strategy here. In particular, I am going to multiply by 1 in a very special way. I'm going to multiply by 1 by multiplying by some fractions within fractions. Alright? And that will allow me to rewrite this limit as such. 3x squared divided by 3x squared is 1. Alright? X squared over 3x squared. By the way, I have to distribute here. Don't forget. So this is going to hit both of these terms down here. Alright, so the first one, x squared over 3x squared, that is 1/3. Plus, so this plus sign here goes here, plus 1 over x to the third, 3x to the third. Squared. Sorry, that's a squared. Alright, now this is something that we can work with. The 1 and the 1/3, they don't care what x is doing. They are what they are. But this part here is going to go to 0. Okay, so I'm going to let x go ahead and go to infinity, which will let this term here go to 0. So now that I'm, in a way, direct substituting in infinity here, I can let my limit operator go away. So then we have 1 over 1/3, which is equal to 3. Okay. What happens if x is going to negative infinity? This line here still applies if the infinity were negative. The first step would have been the same. It's 1 over 3x squared. And when x is going to negative infinity, this term here is still going to 0. Okay, so at the end of the day, same thing happens here. We get 3. So the end behavior is a horizontal asymptote, y equals 3, in both directions. Now what I did here, it's a very common strategy when you're taking limits going to infinity of rational functions. I'm talking about this part here. The clever way in which I multiplied to 1. That'll work for rational functions in general. So I'll write that down. The strategy in general is identify the highest power present, so in the last case it was x squared, and then divide all of the terms by that power of x. Then, armed with the fact that the limit as x goes to infinity of 1 over the x to the n is 0, armed with that fact, we should be able to get the limit pretty easily. So let's try another one. Describe the end behavior of x squared plus 1 over x. And I'm going to work with the top representation, even though the bottom one would technically be easier. There's a reason I put that bottom representation here, which I'll get to in a little bit. So we're wanting limit as x goes to, first we'll do positive infinity. x squared plus 1 over x. I'm going to multiply everything by 1 over x squared. The top is going to need to get distributed. So I've got limit as x goes to infinity of x squared over x squared is 1 plus 1 over x squared. All of that is over x squared, which is x. Alrighty then. When I look at end behavior here, this goes to 0. And as x goes to positive infinity, we're doing 1 plus 0 divided by infinity. Is how we can think about that. And that's going to go to 0. Cool? How about in the negative direction? Limit as x goes to negative infinity of 1 plus 1 over x squared over x. Same idea. X, this part is going to be a small positive number. That goes to 0. But as x becomes a large negative number, the denominator is going to go to negative infinity. So we think of this as 1 plus 0 over negative infinity, which is still 0. Sometimes that negative that pops up could matter during the course of these problems. Okay, so why did I want to write it in this way instead? If you were to do polynomial long division, let me switch colors here. Think back to your pre-calc, doing polynomial long division. Okay, doing this process, this is what you get, x plus 1 over x. Okay, so in general, you'll have, when you divide, you'll have a polynomial plus 1 over whatever that denominator is. And this part here, as x gets really large, that part here goes to 0. Okay, and then x will go to infinity, of course, but it does that in an interesting way. So here's our graph, and look at what is happening as x gets really large. Yes, it's going to negative infinity in this direction and positive infinity in the positive direction, but what we have here is a slant asymptote, specifically at y equals x. So in general, this will work for polynomials of any kind. In general, when you do that polynomial division, you'll have some polynomial here, some polynomial, plus 1 over another polynomial, okay, some other polynomial. Now, 1 over any polynomial goes to 0, because polynomials go to plus or minus infinity at their end behavior. So in a way, you could think of the end behavior of a rational function eventually behaves like a polynomial, because this is going to 0, and then this becomes the behavior that you're seeing, right? For very, very large x, this entire function is very, very close. The y value is very, very close to what it would be in that polynomial. So it's a pretty cool thing. That's more on why you get that slant asymptote when the degree of the denominator is 1 less than the numerator. Let's try a few more examples and see if we can start to piece together a pattern. functions. I've got 3 more functions here. Limit as x goes to infinity, x to the third plus 1 over x to the fourth plus 1. Again, the strategy is identify that x to the fourth is our largest power, and so we're going to divide everything by x to the fourth, also known as multiplying by 1 in a special way. Maybe if the fractions within fractions scare you, you could think of it that way instead. X to the third divided by x to the negative fourth. 3 minus 4 is negative 1, so this is a 1 over x, because this 1 over x is x to the negative 1. Plus 1 over x to the fourth. And then the denominator becomes 1 plus 1 over x to the fourth. Let's see, so what happens? This part will go to 0. This part will go to 0. This is still 1, no matter what x is. And then this one goes to 0. So overall, what's happening is we have 0 plus 0 over 1 plus 0. And what's that? Big fat 0. Right, so this one turned out to be 0. Let's try the next one. And maybe you want to pause the video here and employ this same strategy and see if you can figure out what that limit is on your own before I go over it. Okay, ready? Limit as x goes to infinity, 2x minus 1 over x plus 1. The highest power on x here is 1. Limit as x goes to infinity. This is going to be a plain 2 minus 1 over x. Distributing on the bottom, I'll have a 1 plus 1 over x. So what happens next? As x goes to infinity, this part will go to 0. And this part will also go to 0. And so when x gets really, really large, what we're approaching is 2 over 1. These parts don't go anywhere, which is equal to 2. So think about how this 2 over, there's a 2 here and a 1 here, and then at the end we got to 2 over 1, which is 2. Think about that. Alright, here's another example. Want to pause your video and try it? Alright, here we go. Limit as x goes to infinity of x to the third minus 8 over 1 minus x squared. I got a little bit jumbled here with the amount of space I had. We're multiplying by x to the negative 3 because 3 is the highest power. Okay, dividing everything by x to the third, I'll have 1 minus 8 over x to the third, and then 1 over x to the third minus x squared over x to the third is x. Alright, so what happens? That part goes to 0. That part goes to 0. And as x gets large, this is going to go to 1 minus 0 over 0 minus x is going to positive infinity. So overall, this is 1 over negative infinity, which is 0. Nope, sorry, actually I made a mistake. Let me go back a little bit. Okay, this is 1, this is 8 over x to the third, this is 1 over x to the third, and then x squared over x to the third is actually 1 over x. Okay, so then what do these do at the end behavior? This goes to 0. This goes to 0. This goes to 0. So what do we have? We've got 1 minus 0 over 0 minus 0. And when x is going to infinity, when you're thinking about end behavior, it is okay to have zeros on the denominator as long as your numerator is finite. Because what's happening, as the denominator approaches 0, what you're doing is 1 over a small number, which is a large number. That goes to infinity. Alright? Now, see if you can get what the pattern is. How can we look at the degrees of the polynomials involved in a rational function and the leading coefficients of that rational function to determine what the end behavior is without doing all this work? Can you think about that? Feel free to pause the video and give it some thought. Overall, here's what happens. If you think about how we find that limit by dividing by that highest power, we can predict what the end behavior is going to be. If the degree of the numerator is less than the degree of the denominator, then the limit to infinity is 0. So that is numerator less than denominator. That's like the first one that we did. Okay? And the way I like to visualize this is both x to the third plus 1 and x to the fourth plus 1, both of those want to go infinity, but x to the fourth plus 1 does it stronger. It does it harder. It does it faster. Does it better. Anyways, so the infinity on the bottom is going to win out over the infinity on the top. Because the infinity on the bottom is heavier, it goes to 0. If the degree of the numerator and denominator are equal, then the limit is the ratio of the leading coefficients. You get a horizontal asymptote in that case. That's the second example here. Okay? Dividing by your highest power of x will make everything go to 0, except the highest power is going to go to 1. Okay, so the 2 over 1 here showed up as a 2 over 1 in our answer. And then if the degree of the numerator is greater than the degree of the denominator, then the end behavior is going to go to either positive or negative infinity. Okay, so there's a x to the third minus 8 here. That wants to go to infinity. And the 1 minus x squared wants to go to negative infinity. Yeah? So, you know, I thought I had fixed up all the mistakes in this question. I think we need to think about the signs a little bit. I apologize. Okay, so our degree in the numerator is bigger than the degree of the denominator, so the numerator is going to win. This should be going to an infinity. It's just a matter of, is it positive or is it negative? Now, the numerator is fine. This goes to 0. It doesn't matter which direction it goes to 0 from. But look at the denominator. 1 over x to the third compared to 1 over x. When x is a large positive number, this term, the 1 over x to the third, is way smaller than 1 over x. Right? X is a very large positive number. So these are two very small positive numbers. But this one is bigger. Okay? So this 0 down here is it's a 0 minus a bigger 0. It's a small positive number minus a bigger small positive number. So the denominator is actually going to 0 from below, which means that infinity should have been negative. Okay, so back to what I was trying to show. When the numerator has a bigger degree than the denominator, then the numerator is heavier. It goes to infinity better, faster, stronger. Okay, so in a way it wins. Okay, the numerator pulls the limit up to infinity even though the denominator is trying to drag it down by 0. It's not strong enough to win. So it goes to positive or negative infinity when the degree of the numerator is greater. And you have to not be silly like I was and consider the signs by looking at would the sign of the denominator and the numerator be positive or negative. All right. Can't just do rational functions all the time. Let me fix up my margins right here. All right, x is going to infinity, and then we have a radical divided by a linear. So kind of eyeball checking this. The top is going to behave like an x to the 1/2. And the bottom is going to behave like an x. Right? When x gets really, really big, the things that are being added or subtracted from x start to matter less and less. So this numerator, because 1/2 is less than 1, I feel like the denominator is going to be stronger, and I think this limit is going to get pulled down to 0. So let's see what happens. My strategy here is going to be, I'm still wanting to divide by 1 in a special way, but now I want to contend with this radical as well. I'm actually going to divide by square root of x. All right. Now, when you have the square root of something times 1 over the square root of something else, radicals do merge together over a multiplication like that. So you can write this the square root of a over b, and that's fine. Okay, so square root of x plus 6 divided by square root of x is going to be big square root here. X divided by x is 1 plus 6 over square root of x. Okay. All right, then we have 1 over square root of x divided by, x divided by 1 over square root of x. That's going to be x to the 1/2. That's going to just be square root of x. Because this is a 1 power, this is a negative 1/2 power. So square root of x minus 3 over square root of x. Okay, so there's a bit of a corollary to this fact up here that we talked about before. This will still work if the exponents are rational numbers. So also works for fractional powers. One thing you might have to be careful of is whether or not you don't want to put negatives under a positive root, right? You can't take the square root of a negative number. So you got to watch out for that. But other than that, this will work just fine for fractional powers or square roots. So, what's going on here? This definitely goes to 0. That'll go to 0. And then this is going to infinity. So overall, we have a square root of 1 plus 0 over infinity plus 0. And x is positive, so that's a positive number. Everything here is positive. So this is 1 over infinity, which is going to go to 0. Just like I thought, because the denominator is stronger than the numerator. The power is bigger. All right? A couple more examples. This next one, we're going to do both positive infinity and negative infinity. What I want to multiply by here is, what is the highest power on x? It would be 1 over x. Why is it 1 over x and not x squared? Because if you pretended that the 1 isn't here, if you pretend that that's not here, then the denominator would be absolute value of x times square root of 2, right? So this radical would undo that square, but it would definitely be positive. So I'm going to divide by 1 over x, but on the bottom, I'm going to do square root of 1 over x squared. Actually, this is technically absolute value. But since x is going to infinity, that's positive anyways. Okay, so limit as x goes to infinity of 3x over x is just 3 minus 2 over x. Numerator was easy. Okay, so then the square root of x squared can go inside of that big radical. So in here, you end up with a 2x squared divided by x squared, which is 2, plus 1 over x squared. And then what happens? Well, this part goes to 0, and that part goes to 0. And so overall, if we let x go ahead and shoot off to infinity, we get a 3 on top and a square root of 2 on the bottom. And there's your limit. Okay, and that makes sense because in a way, the numerator and the denominator are of equal strength here. Square root of 2x squared plus 1 is as strong as a square root of x squared, which is an x, or an absolute value of x, and the top is also absolute value of x. So in a way, the numerator and denominator are the same strength here. It's going to get a little bit dicey when we do this for x going to negative infinity. The overall strategy is going to be the same. So I'm cleverly multiplying by 1 because my fraction in the numerator is equal to my fraction in the denominator, just written a little bit of a different way. Okay, now I need a little side note here. When x is going to negative infinity, 1 over absolute value of x is actually going to negate that x. Because x is already negative, right? X is already negative. The absolute value here is going to turn it positive, and when x is negative, negative x is positive. It's kind of a tricky thing there. All right? So what's the difference? What happens? This quantity, let me show that here. This quantity is equal to negative 1 over x, which is, equivalent to what I put here. Okay, so the numerator will be negative 1 over x times 3x is actually going to be a negative 3, then minus negative 1 over x. See how that happens? And then the denominator, all of that is the same. 2 plus 1 over x squared. Right, now what happens? We've got this still goes to 0, and that still goes to 0. And when we go ahead and let x be infinity, we have negative 3 over root 2. Okay, the trickiest part of end behavior is your positive or negative signs. Figuring out what a large negative or large positive x is going to do to all of the different pieces of your function. And that's all I've got for today's video. I would tell a joke about infinity here, but I'm just not sure how it would end. There we have it. Now we know something about end behavior. Keep practicing and have a wonderful day.